Good day to everyone. My name is Andrii Bielinskyi, and today I would like to present our study, which is titled as Complex Systems and Physics Education. I will talk about different aspects of complex systems and which methods should be taught to people who are starting their journey in complex systems modeling. Before I will start, I would like to present you a plan of our presentation. First of all, I want to give an object and motivation of our research. Then I want to present the concept of statistical entropy of Boltzmann and Gibbs, and following from it an extensive statistics. Then I want to say a few words about the V alpha stable distribution for modeling systems with fat tail distribution. Then I will talk about mono and multifractals. I will say about recurrent phenomena and the approach which is known as recurrence quantification analysis. Almost all of you know graph-based approaches, and I will talk about them. And final words will be devoted to irreversibility and my conclusions from all of these methods. In our study, we will present previously mentioned methods on the example of such systems as seismic activity, gravitational wave, and the distribution storm index. For their modeling, we have selected one of the most powerful and modern approaches. The relevance of our research emerges from the world in which we are living. We are living in chaos. Every natural phenomenon in our world is presented to be complex, and it seems that it is unpredictable. Thus, to control phenomena that happen around us, we need reliable instruments for their prediction, and those methods need to know every physicist. In this year, Manabe, Hasselmann, and Parisi were awarded the Nobel Prize in Physics for climate modeling using the theory of complexity. And in our opinion, it's a signal that we should pay more attention to the theory of complex systems. Such complex systems as Earth climate are presented to be dynamic, non-equilibrium, non-Gaussian, chaotic, irreversible, correlated, interconnected, etc. And classical methods that are presented in schools and universities are too idealistic, not so interesting, and unreliable for modeling and prediction. Nowadays, there are a lot of data in the internet, and many systems are presented as time series already in Excel, TXT, CSV formats. As an example, we have chosen the data of seismic activity, gravitational waves, and distribution storm. For your students, you can take much more signals that are very interesting and informative for educational purposes. For further calculations, we have standardized stated signals using logarithmic difference. Here is presented corresponding links that describe this data in more detail. The non-extensive statistics that we will present later were preceded by classical Boltzmann entropy, which was later modified by Gibbs. Boltzmann-Gibbs statistical entropy and related classical statistical mechanics are extremely useful tools in the study of a wide range of simple systems. There is, however, a whole range of natural, artificial, and social systems, which, in contrast to those mentioned, are better characterized in terms of non-extensive statistics developed by Constantino Tsalis. One of the most important indicators here is Q value. When it's greater than 1, our system is presented to be non-extensive. Otherwise, it's extensive or additive. From this slide, we can see empirical distribution of our data, Q Gaussian, standard Gaussian distribution, and the value of Q. We could present the dynamics of other indicators, but we are limited in time. So as you can see, our power law distribution is much more suitable for such signals comparing to usual Gaussian distribution. So as we could see, these three systems have pretty noticeable fat tails in their distribution. We fitted our Q Gaussian distribution and we could see that it fits well. But there is another approach that is suitable for modeling fat tails. That is Levy alpha stable distribution. This type of distribution is described by 4 parameters. Index of stability alpha, which describes heaviness of our tails, parameter beta, which shows how skewed is presented to be our distribution. Scale presents the width of our distribution, and location parameter presents where is located median value. We found that for modeling critical phenomena, parameter alpha is presented to be the best. In this slide, you can see how changes shape of our distribution according to this parameter. For alpha equals 2 is close to normal Gaussian, and the smaller this parameter, the heavier tails we get. These slides demonstrate how changes index of stability during critical phenomena. So Mandelbrot found that many natural social systems does not demonstrate simple geometry. Most of them present self-similar patterns as we study them more deeply. In general, fractals can be any type of infinitely scaled and repeated pattern. Fractal dimension demonstrate how complex is presented to be a studied system, how fluctuations in our signal changes across different scales, and how rough is presented to be studied surface. We also can speak about multifractals. So multifractality is the characteristic of the system to have not only one, but the spectrum of fractal dimensions. For demonstrative purposes, we've chosen alpha max parameter that defines maximal length of our maximal strength of our multifractal spectrum. However, in your physics class, you definitely will find much more other multifractal characteristics. Here you can see how changes alpha max with collapse phenomena for seismic activity, gravitational wave, and our storm index. Recurrence analysis was proposed to study recurrence behavior in the system. The idea here is to plot the array of dots onto two-dimensional matrix, and we consider two trajectories. And if these trajectories are sufficiently close to each other, we put black dot. Otherwise, we put white. We can classify different types of behavior of our system using recurrence plots and its large-scale and small-scale patterns. But usually, we are interested in quantitative measures. Relying on large and small-scale patterns in our plot, we define different quantitative measures. Further, we will present such measure as recurrence rate, but we wanted to mention that other measures must be studied during corresponding courses in complex systems modeling. And here are presented the results for our time series. So many social and natural phenomena can be presented in terms of graph. Using graph, we can get qualitative and quantitative characteristics of interconnection of characters in Bible, or how distributed traits between different countries. For our presentation, we decided to present two approaches that convert time series to graph. One of them is natural visibility graph. According to this approach, we present the values of our time series as nodes, and two nodes are connected if there are no obstacles between them. Another option is to use a recurrence plot or recurrence matrix as a basis for adjacency matrix of our graph. From our graph, we can define different quantitative characteristics. We've decided to choose maximal degree of a node. Here are presented results for our physical systems using visibility graph and recurrence graph. So irreversibility may be associated with complex self-organized processes, which have long-range correlations, non-Gaussian dynamics, etc. And its loss may indicate the development of destructive processes. Our signal can be considered as irreversible or asymmetric if there is some function f that reflects statistical characteristics of a system that differ in forward and backward versions. There is basic methods that should be studied by our students. Very common are Poincare diagrams. We can define irreversibility regarding statistical properties of our graph. But here we've chosen those that are based on permutation patterns and multifractal analysis. Here we can see corresponding empirical results. So we've presented that for physics course, there are interesting systems to investigate. There are a lot of indicators that can give many insights on your system. And during such course, students will have the possibility to study a whole range of different characteristics, such as multifractality, non-extensivity, recurrence, and so on. So, thank you for your attention. Would be glad to answer your questions.